yeah, my name is Taylor McClain, and I'm the Director of Engineering for the Engineering and Interconnection Group here at GridSME. And today we'll kind of be going over the basics of this presentation here is going to be kind of what you're supposed to do ahead of your interconnection request to have the best chance of success. And later today we'll be kind of going over similar topics, but a little more focused on what that actually looks like in the interconnection request package itself when you are in the process of preparing that. As everyone knows, there's been a lot of changes with the FERC 2023 and, CAISO-specific interconnection process enhancements. So we will be touching on a number of those things today. A lot of what we'll discuss is in association with some of those changes, but in general, this is what you should be considering going into any interconnection request. So we'll go ahead and get into this. So first things first is start early. That's always been something that has been suggested, but I think more than ever, it is becoming very apparent that starting early is very important. When I first started doing all of this, there was kind of this throw it against the wall and see what sticks mentality. And the way that things are changing, that's just really not going to be an option. If you want to have a successful project, it's going to be a lot harder to be 2 weeks ahead of an interconnection window and say, hey, I want to get this project connected. So really what this means is your project needs to be more complete than just the very preliminary stages when you go into the interconnection process. For different ISOs, different PTOs, this could mean a number of different things. As many folks are seeing for CAISO, specifically, there are many additional requirements. If anybody's been working in ISO lately, they know that there was a handful of different requirements there, all based around the same idea. But this idea of having a more prepared project is going to vary from ISO to ISO and PTO to PTO. So really, another big thing to touch on with getting started early is just vetting out the viability of your project, because the withdrawal penalties that we're going to be seeing now have become pretty strict. And so it is going to be of much higher importance to just know how viable your project is from a number of different standpoints. Market analysis, have you looked at the POI, how's the capacity looking, PPA as well. There's a bunch of items to really look into, and you need to make sure that you're starting early with looking into that. One of the things we're going to talk about today is the acquiring land, site control. That is really where we're seeing a lot of the the more strict requirements coming in that are going to make it harder for a project to just be built out of nowhere. At this point, pretty much if you don't have 90% land site control going into an interconnection request, it's just going to be very, very difficult to make that work out. So one of the things to know ahead of time is when you're starting early, make sure you're out there tracking down the land and making sure that you have sufficient land for your project. With that, we'll dig into things a bit more. Just a little disclaimer. Today is going to be primarily focused on more of the transmission and the larger distribution level projects. We're not going to go into so much of the fast track, Rule 21, those smaller type projects today. It's going to be focused more on the ISO connections and the higher medium voltage distribution connections with the PTOs. Okay, so another thing to consider when you're going into these into an interconnection request is, are you interconnecting with the ISO or are you interconnecting with the PTO? Because there are going to be different requirements, and more than that, depending on what ISO you're connecting to, there could be additional requirements for a PTO in addition to the requirements for the ISO. Typically, that's not the case, but as we've seen for places such as New York ISO, National Grid actually has a handful of additional more strict requirements than what NISO requires. And so if you aren't on top of those requirements ahead of getting into the NISO interconnection request queue, then that could actually put your project at jeopardy as well. So there should really be a focus on not only vetting out the viability of your project going into it, but understanding what interconnection process you're going to be involved in and who are all the players in those different interconnection processes. Because it isn't ideal to just assume that if you're connecting to the ISO, there's going to be no PTO involvement, because that just might not be the case. So for something that a lot of our clients are interested in going into things is that when you're trying to determine what project you want to submit to an ISO PTO, it's figuring out that POI, and there are so many different ways to kind of hone in on that. We found that there's not really one right way to do it, but typically there's a right way based on what information or what details you might have for your project going into this process. So what we're going to start with is kind of like the two highest level places to start with these things. And typically that's looking at available land. Do you have a site in mind that you're interested in? Because that kind of guides where your interconnection is probably going to end up. Or are you more interested in an ISO or a PTO or an overall region? And therefore, is it more pertinent to start with the available system capacity at a potential POI? And these are typically the ways that you're going to start narrowing things down. And so we're going to jump into a little bit about that. So if you're starting with available land or project site, as I kind of mentioned, that really narrows down your POIs based on what's in close proximity. We see projects such as geothermal, wind sometimes have these longer generation tie lines, but for the most part, when we're looking at solar, battery, or other types of generation, we're typically looking to stay within, maybe 1 to 5 miles, 5 miles being on the high side, away from the POI. For your gen tie to run, because it just really hurts the viability of the project unless you're talking about constructing a very large project. So if you're starting with the available land that you have, really what you're going to want to look for first is what is the lowest cost to physically interconnect to a location. And that could be, as mentioned, the proximity of your site to a potential POI. In looking at this, a lot of folks might overlook the fact that it's all great if you can run a gen tie and it's not too long, but you should also be starting to consider the right-of-ways that might be involved in that. If you're crossing a number of different pieces of land that are owned by different folks, it's good to think ahead of time and understand that you're going to have to work out getting your gen tie built with each of those entities that owns the land in those segments. So having a little bit better of an understanding of how you're going to run your gen tie is pretty important, and so that is something that can be taken into consideration when you're looking at a potential point of interconnection, starting with the available land. So with available land too, what we're also going to be considering is, do you want to connect to a substation or do you want to connect to a line? What we see most of the time is that it's getting harder and harder to find a piece of land near a substation within that gen tie length sweet spot, and it's also becoming more congested at a lot of substations to try and get into the substations. So we do see that a lot of folks are going out and finding land where a transmission line runs right through it. And so when we're starting with land locations, we're going to look at, do you want to interconnect to a substation or do you want to interconnect to a line? And if we're looking at the substation, we're going to look for available breakers. We're going to look for the ability to expand the substation if there are no breaker positions available, and how congested that substation is, meaning are there a lot of transmission lines, distribution lines running around that you're going to have to go underground to get into the substation, or you're going to be moving lines or running over lines, because these things, in some cases, they can make it impossible to get into a substation, and in other cases, it just means a higher cost to interconnect. So going back to, considering the lowest cost to physically interconnect, when we start to see these features such as a substation with a bunch of transmission lines around it, that is definitely a negative as far as considering that substation for a POI. And so if we are looking at a substation POI, while under the perfect conditions where there's an available breaker and there's the ability to get your gen tie in, while that can be a cheaper cost to interconnect, it's not as typical that we're finding that these days. So that's when we are moving towards looking at interconnecting to a line. The most immediate downside to interconnecting to a line is that you're going to get in or to interconnect to that line. There used to be a time when you could just tap a line and that was how you interconnected. But at this point, what we're really looking at is a 3-breaker ring bus at a minimum to be able to interconnect. And when we start looking at and narrowing down potential points of interconnection from a land availability perspective from your site, we also now have to consider, is there sufficient space to build this 3-breaker ring bus? How close are you to a substation? That's actually an important one for a number of utilities where they actually specify you have to be a certain distance away from the substation. For example, if you're interconnecting to IPCO, if you're within 2.5 miles of a substation, they will not let you interconnect to a line as a POI. So that's kind of something that you can look into very immediately to vet out the viability of a project, because let's say you're 2 miles away, that becomes a difficult interconnect if you need to run that 2-mile gen tie all the way to the substation, and it also puts you out of the running to interconnect to the line right there. So if you're starting from a land, a point of view of having the land, having your site and wanting to go from there, then definitely taking into consideration how far you are from substations is important, and making sure that you have sufficient space to build that interconnection facility as well. So the next couple of slides, I'm going to go over a couple of the things we kind of look at and what we were talking about. This is just a quick little done-up example of what a nice gen tie might look like. You got your project site, which is fairly close to the substation where you want to interconnect. You're only crossing over potentially one other person's piece of land, so obtaining right-of-ways is going to be a lot easier. And ultimately getting into the substation, you're close by. So this is kind of what you would hope for in a best-case scenario, knowing that it isn't always viable to find a piece of land this close to a substation. So looking at this example here, this is a substation, and I just kind of wanted to point out the ways that you might be able to look at a substation and see how viable it is for an interconnection with the least amount of updates needed. So looking at the first blue marker there, that's a breaker right there, and the full setup of 3 breakers represents the 1.5-breaker scheme. And so in evaluating this substation, we can see that in the bottom 2 1.5-breaker locations, there's 2 available positions, or apparently available positions. They could be claimed by higher Q generation. There's a number of factors that you would have to consider to determine whether you felt like that would be available for your project when you interconnect. But as an initial first pass and high level look, if you go looking at a substation and you can find these open breaker positions where there's no breaker installed in a 1.5-breaker scheme or other, this starts to give you kind of a good understanding that this could be a good substation to consider as a POI. So moving on to this is kind of, this is an example of what I was talking about earlier as far as a substation being congested. I've gone in and kind of highlighted some of the lines coming in and out of the substation. And as you can see, on just about every side of the substation, there are transmission lines run. And this would be an instance where going underground is probably going to be the only way that you get into a substation like this, potentially going over the lines. Regardless of what it might be, it does mean that this is going to be a much harder situation to consider this substation as a potential point of interconnection. So if we were to see something like this, and we were in the process of filtering down potential points of interconnection, this would definitely receive more of a negative rating, and would be considered a site that we would want to look at only if we ran out of other possibilities.
Hey, Taylor, we've got one question.
Mm-hmm.
Can you provide examples of TOs that allow for a BAAH scheme? How does it compare cost-wise to the 3-breaker ring?
So actually, I mean, I don't think you can do, because, sorry, with the breaker and a half scheme, that would actually only allow for the interconnection of your line and then one other line out of it. So that wouldn't be a viable way to interconnect any project. So what I do know is that most utilities are going to require a 3-breaker ring bus, which actually I'll show this. So this is an example of actually a ring setup with 4 breakers. But the 3-breaker ring bus is basically set up so there's a position for your gen-tie to interconnect and 2 positions for the existing line to come in and then come out. Sometimes you'll hear it called a loop-in station. With the breaker and a half configuration, the way that's set up is there's just 2 locations for lines to interconnect. So a breaker and a half wouldn't be allowed at all as a way to interconnect. And for the 3-breaker ring bus, that's definitely more of the standard. With every so often I've seen a 5-breaker ring bus required, and I think that's just the utility preference for ability to expand further in the future, because obviously if it's a 5-breaker ring bus, then you have more positions for interconnecting other parts of either the system or other projects. So I would say that typically it is going to be a 3-breaker. And then Sarah, was the other part of the question cost on that?
The question was, can you provide examples of TOs that allow for a BAAH scheme? And then the second part was, how does it compare cost-wise to the 3-breaker ring?
Oh, okay, yeah. So, I mean, equipment-wise, I mean, it's actually not that different. The 3-breaker ring bus is going to cost more. It's going to take up more space. I mean, if we're talking about expanding a substation to put in a breaker and a half scheme or an additional breaker and a half scheme, that could likely be less expensive than building a 3-breaker ring bus substation, just based on the fact that there's potential that at a substation there might already be the space at the substation to fit an additional breaker and a half scheme. We know that from looking at like California utilities per unit cost guides, you're probably looking somewhere in the $10 to $15 million range to build a 3-breaker ring bus. So it's definitely something to really vet out at the beginning if you have a project, because or if you have a project that has a line interconnection, because at 10 to 15 million, depending on voltage level, you know, that really means that you probably want to be in the 100 megawatt, 50 to 100 megawatt range immediately at the beginning, just to kind of make that cost work out. It can offset some of the costs because ideally you won't really be running much of a gen-tie. So there are savings in certain areas, but the 3-breaker ring bus can definitely be an expensive option to interconnect. And so here, this was an example I just wanted to kind of pull together. This isn't exactly a 3-breaker ring bus position or setup, but it's similar. And so you could expect for 230 kV that you're going to need, you know, upwards of potentially an acre to fit all of that, probably a little bit less. That's something that you need to be considering, because if you chose your piece of land where a transmission line runs through, you need to be then considering, do you have sufficient land to fit your project? And then also, do you have sufficient land to fit your 3-breaker interconnection facilities? And obviously part of your project will be your substation, your main power transformer, your collector station, all of that. And so this kind of just shows that, you know, for 3 transformers, you're looking at about a 1/4 acre. So really, to be on the safe side, you probably want to put aside, an acre plus to account for your interconnection facilities, 1 acre to 2 acres. Okay, so, excuse me. So for starting with the capacity, or the system capacity in place of the land position, this is typically, if you don't have a piece of land that you've already gone and vetted out and tracked down and you have a lease for, or you own in some shape, then typically it can actually be a better place to start by evaluating the capacity on the system. And this can be done in a number of ways. You could look at doing a very high level system-wide approach, which can take a number of iterations and not be quite as accurate, or you can have a list of the POIs that you want to consider and then do a handful of contingency analyses and evaluating the impacts of the project at different sizes at the POI to find out what the likelihood of the system is to be able to support your project without the need for network upgrades. So with this approach, what you're really looking for is voltage issues and thermal overloads in the PowerFlow software, whatever you're using, and you're going to try and target a project size that, for all of the evaluated contingency conditions and for the normal operating conditions, there are either the least amount or there are no thermal overloads or voltage issues. So it's not to say that if there are thermal overloads that your project is not going to be viable, but it does mean that pretty immediately you can consider that a higher cost to interconnect. And so starting with the system available capacity approach to narrow things down can be helpful if you just don't really have an idea of where your land is going to go, and you can kind of start by looking at what are the most viable POIs. This is ultimately going to come into play when you start with your project land as well. Oftentimes we'll see folks go evaluate my land for a good POI and then evaluate the POI to see what the capacity is there. But this is kind of the step that makes it a little bit easier to start if you don't have land. One thing I do want to know on the land too is that the land will limit your project size. So if you do have your land going ahead of going into the capacity study, then that is very helpful, because you can kind of say, well, instead of targeting a 500 megawatt project, my land only allows for 100 megawatts. So you already know that there's a smaller range to be working in. The two definitely work together hand in hand. So looking at this, when does a site assessment make sense for most folks? When you have land and you just don't know what POIs are nearby, or like I was mentioning just a little bit ago, if you are unsure of how much you can fit on your on the land that you have, it would be good to start with a site assessment. You can kind of evaluate, like, I really wanted to put 100 megawatts of solar here, but considering the acreage constraints, I'm actually only going to be able to fit 50. And this definitely starts pointing your project in the direction of what's viable and what's not. So if you've completed a capacity analysis ahead of this, this can then be used to further determine the bounds of your project size. And once again, determine the viability of your project as it may differ from the idea that you had going into this, and what the land and the POI can actually support. So starting with the available system capacity, I was talking on this a little bit ahead earlier, but if you're starting with the system capacity, then once again, you're going to be looking at thermal overloads and voltage violations. These are the most immediate aspects that you want to consider for a capacity analysis and for evaluating the system capacity. This is something that is going to provide you kind of a range of understanding of what might be the least cost interconnect or a positive POI. It should be noted that in doing these capacity analyses, they don't aim to do exactly what the utility is going to do. There's a lot of factors that could be different when that comes around. But what it does aim to do is cover most of what the utility is going to be looking at, which is your normal and your emergency conditions, running a number of contingency analyses. That's basically to see like, hey, maybe you can fit your 50 megawatt project at a POI, no problem, when all of the lines are in service. But you go ahead and start taking elements out of service, and you might find that there are issues on the system. So when you're looking at these available system capacities as well, it's very pertinent to either get the latest and greatest base case from a utility, or it might be necessary to find the best base case that you can and review the active queue generation at or near your POI, and go ahead and model that to stress the system and see what potential issues there might be that aren't related just to your project, but are going to be related to your project along with other projects. Other things to consider are transmission plan upgrades. So with the system capacity analyses, typically a number of different scenarios will be evaluated to kind of get the range of possible results, so that you can have a good understanding of, or a better understanding of the risk of going into this with your project, and whether or not you're going to be able to interconnect your project at the megawatts that you really want to. Because obviously the project size plays a lot into things. If you have a larger project and you can fit that without network upgrades, then that helps to offset in the long run some of the other costs, such as running a potentially longer gen tie or building that 3-breaker ring bus. So it's important to know going into this what project size is realistic to target, because it could turn out, if you find out later on that you have to downsize from a 200 megawatt project to a 100 megawatt project, even if you can do that downsize, at that point, that could end up ruining the viability of your project. So looking into this a little bit ahead of time can be very helpful. So for starting with this, as I kind of mentioned before, this is definitely the best place to start if you are pursuing a wide range of areas, or you have a number of different POIs that you want to consider, and you're going to be tracking down land at a later time. Another thing to talk about on this one is you can also evaluate the different voltage levels when you're looking at this. When you're looking at everything from a land standpoint, you're really looking at, you could look at one substation and it might not necessarily consider whether the 230 kV is the optimal point, or maybe the 115 kV is the optimal point. And so even if you have a substation kind of pinned down, a capacity study could make sense to take a look and say, hey, I'm interested in this substation, but I want to know where the best bang for my buck is going to be. Is it going to be at the 230, or does it make sense to just stick with the lower voltage level, save some costs on the equipment to interconnect, and potentially the available capacities are similar. So items like that will definitely be looked at and will be addressed in a capacity analysis. If you have the land already ahead of doing a capacity analysis, typically at that point you would be starting with the bounds provided by the land that you had. And so this will then tell you if there are further limitations on your available, or on the size of your project based on the available capacity. So more talking about land, there are going to be different requirements for, potentially for each of the PTOs, each of the ISOs. So it's good to go ahead and look into their requirements ahead of time. But looking at the range of requirements posted by ISOs and RTOs, typically what you're going to be looking at is either 5 to 6 acres per megawatt for solar, either 0.06 acres per megawatt or 1 acre per 100 megawatts for battery storage, or 30 acres per megawatt for wind. And this doesn't mean that you have to stick to these requirements. But if you do have less land for the project size that you choose, and you want to submit that project still, you are going to have to provide some amount of justification for that. And that comes in different forms for different ISOs and different PTOs. But it is something that you definitely need to consider. It's not going to set you back from using the land or anything, or it's not going to necessarily stop you, but you're going to have good justification for that. And further, if it really isn't feasible to fit that project size on your land, it's just not going to be a good idea to interconnect, because that will ultimately unfold. So starting with trying to meet these requirements is definitely in your best interest. Okay, so for the next sections here, we're kind of going to talk about the planned operation of your facility and things that you might want to be considering ahead of time before going into your interconnection request, based on how you plan to operate the facility when it's constructed. This is something that I think we've found historically a lot of folks aren't thinking about until they hit like the NRI process, the new resource implementation process. They're looking at getting into as-builts and really starting to procure equipment and get these final designs going. And there can oftentimes be a lot of aspects that were overlooked in the initial preparation of the application and the project. So what we try and suggest is really considering things that even seem very far out for the project as early as possible, because basically anything that you can pin down ahead of time, or at least have a slightly better understanding of ahead of time, is going to help the project flow a lot more seamlessly throughout the process. So here, we will end up talking about BESS a lot. There's a lot of folks building BESS, and there's a lot of things that are specific to battery storage and the functionality of it that aren't often considered ahead of time. For instance, especially with a standalone BESS facility, if you want to be able to offer RA or ancillary services, you're going to need to have deliverability. And there's certain processes where you might end up going into something with an energy-only battery project. And if you're not paying attention to that and thinking about how you want to operate your facility, for instance, if you're doing an MMA to add battery storage to another project, going in with an energy-only battery storage project might just completely be an unviable thing for how you plan to utilize the BESS. So with BESS in specific, we do want to make sure that there is some focus on having that deliverability capability, having the capacity, and ultimately being able to operate the facility in the form that you want to. The next kind of big thing that we've seen hold up some projects is determining whether they want to be co-located or hybrid. And if you can kind of get a grip on which approach is going to work best for you earlier in the process, then that's definitely going to be a good place to start. It's definitely not to say that you need to know when you first submit your interconnection request that it's going to be co-located or it's going to be hybrid, but that will affect things such as your metering schemes, and it will have an impact on, how functional the project can be, if it's AC coupled versus DC coupled, and also thinking about these things. If you have a DC coupled project and then you ultimately go to split it out later on with as an AC coupled project, then that's a decision point where at that time you need to decide whether it will be co-located or hybrid. But if you're starting with an AC coupled, then it might be a good idea to just start considering ahead of time what's going to work best for you. Do you need 2 resource IDs? How are you going to be marketing your energy? What kind of services are you going to be offering? Okay, with AC coupled, all right. Sorry, just reading that question. A typical diagram. Yeah, let me see. One sec. I don't know if I have a great diagram immediately available for the AC coupled. But I will try and explain that when I get to some of the diagrams for just a single generator here in a little bit. and see if I can pull up an AC coupled in the meantime. But the AC coupled design is basically going to be that you have two separate types of inverters. I mean, let's say we're talking about a solar and PV and battery storage hybrid facility. Rather than having both the PV and the battery storage connected on the DC side of a single inverter, now you will have a storage inverter and you will have a solar inverter. And what this basically allows for physically is now, instead of having to locate the battery storage everywhere throughout your PV facility where each of the inverters is located, you can now have your battery a little bit more centralized. And it also just allows you more functionality for how you're going to market the project, because in this sense, I mean, a lot of folks actually specify DC coupled systems without a bidirectional inverter. And if you don't have a bidirectional inverter and you want to be able to charge from the grid, it just won't be possible. And so we're seeing that AC coupled is definitely preferred over DC coupled, at least for what more people are submitting. And the AC coupled is just going to, while it will be more expensive in the sense that you are going to essentially be building two facilities at the same location, you end up with a lot more optionality on how you can function the facility. So yeah, I'll see about getting an AC coupled diagram pulled up in a little bit. So another thing to think about going into this is, are you going to grid charge? As I was mentioning just a little bit ago, if you don't have a bidirectional inverter, if you have a DC coupled facility, then you're looking at a setup where you won't be grid charging. And so you have to kind of think about this ahead of time. And if that is a functionality that you're going to want, what that also means is that you're going to be studied by the utility as a load at some point if you do want the grid charging capability. So that could potentially come with additional restrictions or additional costs to interconnect if you opt for grid charging. So definitely something that you want to be thinking about ahead of time, because it will change the overall design. And if you do want a grid charge and you want DC coupled, then you know ahead of time that you need to be specifying storage type inverter, a bidirectional inverter, so that you can both discharge and charge the batteries that way. Another thing that you need to be considering at this point is the auxiliary load as well. This is more pertinent for battery storage because we're seeing those high auxiliary loads for the HVAC systems, but it does apply for other projects as well. But we'll kind of focus this discussion on the storage. When you're looking at potentially megawatts of auxiliary load, you definitely need to think about how that's going to get fed. And what we're seeing in certain cases is the local PTO actually has the first right of refusal to feed that load. And so in some cases, we've even seen instances where you may have been planning to feed your load from your system, but the local PTO is saying, hey, no, we're going to be feeding this. And so that kind of alters your design, and it also alters how overbuilt your project needs to be, because if your load is being fed from a separate distribution source, then you don't have to factor in the additional load when you're determining how many inverters you need to install to meet your megawatts and your reactive power requirements. And another really important thing to consider here is, or start thinking about, is that your metering schemes are going to differ a lot depending on whether you're doing DC or AC coupled, whether you're planning to grid charge or not, how your aux load is going to be able to be set up. In a lot of cases, you're going to have to monitor your aux load for battery storage system. So there can just be a lot more that goes into the metering schemes depending on what type of project you have. So it's definitely good to start thinking about that early. And Sarah, it looked like I'd seen a couple of, or another question come through.
Yeah, I think you answered them both, but they're both from Jitendra, and one was, can you guide on metering with AC coupled, and any typical diagram will help. And then the follow-up to that, is it possible to consider both PV charging and grid charging with AC coupled? And will it change interconnection study considering single common POI for both PV and BESS? And I think you may have answered them both.
Okay, yeah, I guess I'll just go into the second one a little bit more. It would be possible to do grid charging for AC coupled. I mean, typically that's the reason to do AC coupled. With going DC coupled, you're getting a couple of advantages because especially if you're not choosing to charge from the grid, you now have less inverters installed at your facility, which is a less MVA installed capacity, a lower MVA installed capacity, and therefore a lower short circuit contribution. So you're saving in some potential impacts to the grid in that way. And then if you're also not charging from the grid, then you are also avoiding that load study, which could potentially either result in needing to build upgrades to charge if you're choosing firm charging, or if you're going with as available, then you could end up in a situation where you're just not able to charge with the way that the grid is currently focused. If you're going with the AC coupled or DC coupled, I mean, you can set up either so that you could charge from the grid, but the AC coupled setup definitely gives you a little bit more optionality with how your project functions, and you could be, you can still charge from the grid and from the solar. It's just that if you're charging AC coupled, the solar is going to have to go through the system to the collector station bus. And we'll look at a diagram here a little bit later in the presentation. And then get fed to the battery to charge it there. So there would be more losses for charging your battery in an AC coupled system, which could be a potential downside as well. So here we'll so this was, I wanted to go into another topic that we don't always think about, which is determining how much you want to submit to the utility for the study or the load study for your charging scenario. This just kind of shows the representation of when you're considering charging at the gen terminals. If you submit and you say, I want to be able to charge 100 megawatts at my generator terminals, what you're really telling the utility is that you want them to study you for 102 megawatts at the POI. So if you're concerned about going over your 100 megawatt project size, what you would really need to do is submit for a project where you're charging for 100 megawatts at the POI and only getting 98 at your terminals, at your gen terminals. And what that means is it's just going to take you a bit longer to charge your battery back to full than it would if you had them study you at this value, because here you'll be injecting 100 megawatts at the terminals, or more than 100. You'll be injecting about 102 megawatts at the terminals to get 100 megawatts at the POI, and then if you're only charging at 98, there's a 4 megawatt difference. So you aren't going to have that exact 2 hour, 4 hour, whatever capacity your battery is, time frame to charge if you opt to be studied for a lower amount at the POI. And while we're here looking at these diagrams, basically if you were AC coupled, you would see that the main power transformer MV bus, the 34.5 kV where the load is located, you would have another feed off of there to all of your solar, or you'd have two feeds off of there, one to your solar and one to your battery, and that's where they would interconnect. So you can imagine that if you are charging your battery from your solar, you are going to experience all those losses through that part of the system to charge your battery. Whereas with the DC coupled, you're going to have everything connected on the DC side and you won't experience those losses. But what is going to happen is, as I mentioned earlier, you're now, if you have a very large project, this could be an issue, because now you're going to have to put all of your battery modules spread throughout your solar field to be connected on the DC side of your inverters. And so for these bigger projects, going with DC coupled can sometimes be a little bit less ideal, but that all kind of comes down to what your operating strategy is And if those additional costs to construct and have everything spread out like that is worth it for your project operation. So another thing to consider is the timeline to construct versus your time in the queue, and just the timeline of the project overall. Historically, up until all of the transition cluster changes, this hasn't been a huge deal. Unfortunately, as most people know, there's been so much backlog in the queue that it's never really been, or as of recent, it hasn't been too much of an issue to consider whether you can get your project constructed in the timeline that's allowed, because typically what's happening is you're trying to construct your project faster than the utilities are letting you construct it. But it should be kept in mind that the whole idea of these changes, the FERC Order 2023 and all the changes that the ISOs and PTOs are putting into place, is that ideally it is going to free up the space in the queue. And if we start to free up the space in the queue, where we could very likely end up back in a place where if you're submitting a project, you're not going to be arguing with the utility about trying to get an earlier date. You might be now looking at a point where whatever COD you submit to start is something that you really need to stick with. And so when we're evaluating these CODs and things like this ahead of time, when you submit this initial interconnection request package, you definitely need to start thinking about how long is it going to take you to procure equipment, because as we know, the time to procure has gotten very backlogged. Particularly circuit breakers are one. We've heard a lot of utilities mentioning they're having issues with procuring, and so that's going to be a problem across the board for folks. And so this not only comes into play with the design of your facility as well, but if there are potential network upgrades where circuit breakers have to be replaced, that's going to be a little bit less out of your, or a little bit more out of your hands. But when you're starting these interconnection request packages, it's very important to kind of look at how long it's going to take you to procure your equipment, and does that allow you to meet the timeline that you're presenting to the utility. Yeah. So another thing to consider when you're looking at the design of your facility and going into this is how you're going to meet the reactive power requirement. And so FERC Order 827 is what basically defines the power factor requirements to be met. This can be different from ISO, RTO, and PTO. Typically, it is the, I think most people have probably heard for the IBR generation, it's the plus minus 0.95 at the high side of the main power transformer. That is most often what you're going to see, but there are some outliers like LADWP, who requires basically an additional 20% reactive power, and some other folks who require that reactive power range to be met within a certain voltage range, which further stresses it. So what you should know is that no matter what, your bare minimum going into it is that you have to meet 0.95 to 0.95 lagging at the high side of the main power transformer. And this additionally, you also, for the inverter-based resources, you have to meet this 0.95 plus or minus range at the generator terminals as well. What this means is basically you can have a capacitor bank. Actually, here, let's go here. So what this is saying is that you have to have enough inverters installed to be able to meet your full megawatts at the POI while also operating in the plus minus 0.95 power factor range. And you have to also be able to meet that at the high side of the MPT. So for any of the losses between your generator terminals and the high side of your main power transformer, you could use a capacitor bank to make up for those losses. But if you can't even meet the 0.95 at the generator terminals, then your project is going to have to be redesigned to have more inverters. So this kind of circles back around at some point to be defined by how much land you have, which is defining how many inverters you can have. So FERC Order 2027 and 827 and the requirements there are going to define how big your project can be as well. So you do want to start considering at this stage in the project how you're going to meet the power factor requirements, whether a capacitor bank is going to be required, and those factors that go into meeting the power factor requirement. So here we kind of just talked about those key elements of the of your decision points. I wanted to also go into the transition cluster in general, because there are a lot of changes that have been happening. Once again, I think it is very important to note the start early from the beginning of these slides. In the past, we used to kind of get reached out to maybe a couple weeks before a cluster window and say, hey, like, we're considering, interconnecting here. What do you think about that? And can we get this application going? And we would just like to suggest that that's going to be a really hard way to guarantee that your project is going to be successful, and that it's going to be viable. So trying to start as early as possible is going to be very, very key with these transition cluster projects and everything moving forward. The other thing, as we mentioned before, is site control. This is such an important aspect of a project with, the reality now is that if you don't have site control, you don't really have a viable project. So this should be one of the main focuses ahead of getting into your project, and something that you need to put a lot of importance on. Another thing to consider is everything we've kind of discussed today, the preliminary steps you can take to determine to better determine the viability of your project. Not only are there consultants out there who can do these high-level capacity analyses, do these site assessments like GridSME does, you can also go to the PTO and submit a pre-application report, which gets you real-time and accurate data on a potential POI. So there's a lot of work that can be done ahead of getting into the interconnection process to just give you more confidence in the viability of your POI, which could lead to more confidence in going out and obtaining that site control. So it's important to understand the viability of your POI. And another thing to consider is that detailed site plans are very likely going to become the norm. Up until now, it has kind of typically been that you need to show a site plan that kind of defines the project boundary, shows where your gen tie is going to run, and then references the POI. That's still the case in a number of places, but what we're finding is that for a number of utilities such as NYSO, they are really requiring that you have a very detailed or a more detailed site plan than just a box around your site and a gen tie. They want to see solar panel layouts. They want to see, where your battery modules are going to be. So at this point, it's really not a bad idea to just start considering that maybe a detailed site plan becomes a part of vetting out your location and your land for viability, because it is an additional step to take up front, but it could save you a lot of headache later in the process if you're able to kind of sort out some of these potential setbacks to your project before you get too far into it. So definitely keep an eye out for the detailed site plans to be coming. So since cluster 15 resubmissions are on us, I think it's important to go into a little bit about talking about the cluster 15 specifics. One of the big things we've been getting questions on is the scoring criteria. And so that's something that you should definitely be preparing for and looking into. The way that CAISO is doing things is, they're going to have they have the scoring criteria set up such that not only is your project going to be vetted out as to whether it's in a TPD zone or a merchant zone for its viability, but now you have your own internal scoring that you're going to be applying to your project. And a lot of this is based around the completeness of your project and a number of other factors. But you basically, at this point, need to be considering the additional scoring criteria for CAISO and deciding, do you really want to put in the additional time to boost your score? These types of things can be done by providing a more detailed site plan, providing more well thought out single line diagrams, which are more realistic of the project that's actually going to be built. So now there's kind of additional steps you can take if you need to try and prove how much more viable your project might be. As I was mentioning, we have the merchant and transmission, the TPD zones, transmission planning deliverability. This is basically setting it up so that if you are in a merchant zone, you are going to be energy only. So this is a really, really important thing to look at ahead of time. As we discussed earlier in the slides, having the capability to have deliverability is very important for the viability of a lot of projects, particularly battery storage. So if you do find that your project is in a merchant zone, and that isn't going to work for the planned operation of your facility, you could still apply for deliverability in the annual window, but this is a really pretty big setback immediately for your project. So you need to be paying attention to whether you're in a merchant zone or a TPD zone right off the bat, and deciding whether it still makes sense for you to submit your project if you are in a merchant zone. One of the other big changes is now we have the GRIP system. We have been working through this, and as with any new system, there are typically issues. So once again, it's just advised to start early with uploading and getting things onto GRIP, and just training and practicing with GRIP itself, and understanding that there is the likelihood for technical difficulties. So leaving submissions and things like that up to the last minute is not going to be a good idea, especially considering the new system. And so with that, I think we'll go ahead and open it up to just general Q&A, if anybody has anything.
Great, thanks, Taylor. And for all the participants, I am going to give you the ability to unmute yourself. So if you do have a question and you want to just ask it, go right ahead, or you can raise your hand, or again, you can type it in chat.
Hey, Taylor, this is Divya. One question initially that you talked about co-located versus hybrid. Can you talk about the difference, and is that different between every ISO? Because I thought the recent New York ISO, we were actually hybrid, but they had us classify us as CSR. Can you talk about that a little bit?
Yeah, so it is different between the ISOs, and so it is something you're going to want to know specific to each one. The co-located is basically setting you up with two resource IDs, and this kind of becomes more pertinent when you're looking at the functionality of your storage component and how you want to be able to operate that. Having the two resource IDs gives you a little bit more flexibility on that. I will admit I'm not the expert on this. I would say when it comes to stuff like this, talking to folks with an NRI department, somebody who is dealing with the projects at a later date when they are starting to go through that, they'll probably definitely know more. If you do have specific questions, I'd be happy to pass them on to our NRI group as well. But yeah, basically that is going to differ from PTO or from ISO to ISO. And you do need to, the hybrid is going to just have one resource ID for both facilities. And so it could limit you in your overall functionality of your facility. Yeah.
Sorry, we're in the same room. Okay. Getting that feedback because you have sound.
So Casey, if you're in the same room, go ahead and mute yourself and then just talk through Taylor's mic. Sorry about that, everybody. All right, Taylor, you can unmute.
Sorry, here we go.
Sorry about that. Hey, my name is Casey James. I'm not a metering expert. Not super NRI.
Yeah.
First day today, so whatever. So yeah, the co-located versus hybrid, the two resources versus one resource, single metering point for hybrid resource, two metering points for co-located. The other thing that BESS opens you up to is so you can get your standalone BESS, and so you can get your ancillary services provided strictly for the BESS purpose. Also, the other thing is the renewable energy credits. If you're going to sign up for Regis or SGIP and you're going to go for REX, metering as a co-located resource makes sure that your renewable energy is parsed off from us. If you have a co-located or if you have a hybrid resource, the Regis program won't have a way to delineate what's happening at the individual component level. And so what they do is they'll just take all the comings and goings of the entire site, add them and subtract them, which doesn't take into account round trip efficiency losses that you might incur from the BESS. So sometimes you can see a 15% cut of your actual renewable energy credits if you decide to go hybrid. So it's in that way, it's financially encouraged to go with a co-located resource. But that's like the biggest difference that I see, the biggest difference that
Hey, thanks for
Thank you, Casey.
Nice. Good being in
Great.
the office.
Thanks, Casey. Thanks, Taylor. So we do have another question that came through chat. Can you clarify tolling agreement versus non-tolling agreement of BES? Does it change BES application?
I actually can't. I don't know that, but I know we would be happy to take down that question and get back to you on that. Sorry about that.
Yeah, great. No, Jitendra, we will definitely find out the answer and we will get you clarification. Are there any other questions from participants?
Sorry, I got one question here. Can you guys hear me?
Barely.
Is this better?
Yeah.
Okay. Question was regarding that you mentioned about the power factor requirement meeting the power factor at the high side of the transformer. Is there any push instead of defining power factor to actually define reactive power instead of a power factor by that the generation facility has to meet?
I mean, I don't think so. I mean, they are kind of interchangeable. The power factor just defines the amount of the reactive power that's needed based on the size of the facility. So, I mean, FERC 827 went into place in 2016, I think, and there have been some changes, but I mean, it's generally remained the same. So I don't think there's any change or any plan to kind of change how it's defined with that 0.95 power factor range. And then obviously, like I had mentioned before, a certain PTO or ISO could require a higher amount of reactive power. But once again, we typically see that specified in the power factor range rather than as an MVAR amount. But they really are ultimately interchangeable.
Okay, thank you.
Just to chime in a little more, this is Ryan Hancock with GridSME. For 827, there are kind of specific requirements on your reactive power and where it comes from, if it's a dynamic device or if it's a static device. So it definitely does play an important role in all of this. And there are ways to kind of supplement it within the confines of 827. So if that helps kind of provide any additional clarification on that question.
Yeah, no, thank you.
Okay, one last question from me. On the aux load, so typically we've been doing where it is getting charged as part of the project as the load. You said that if we could identify a secondary power source, how common is it to identify it early at this stage? If there is an additional distribution line?
Yeah, it is difficult, and that would really come down to starting a conversation with the PTO or the ISO separately. And as we know, that can be difficult at times. It's not always easy to get a chance to have a conversation with either all the time. But that would really be the place to start there. I guess what I should have mentioned is it's always best to, and I guess I'll go into this a bit more in the discussion later this afternoon, but it's definitely best to assume that it won't be fed from a local utility to start. That way you can overbuild your design and plan for that. And then as you determine these things later down the line, you could start, adjusting your design. It's always easier to remove equipment than it is to add equipment. But yeah, unfortunately, to really understand how that final feed is going to work, you would need to start getting some input from the PTO realistically to help you guide that decision.
Okay, thank you.
Great questions, everybody. Do we have any other final questions? Great. Well, we will go ahead and wrap up this webinar today. We do have a follow-up webinar this afternoon with more specifics on how to make your interconnection successful. Tomorrow, we also have several sessions regarding the CAISO NRI process, as well as metering and best practices regarding getting through the buckets, as well as getting your point-to-point testing and metering accomplished. And on Wednesday, we will be talking about NERC, specifically cybersecurity, GO and GOP requirements, and what's new with standards that are coming up in the future. And we will be sending out a survey. Tori posted that link in chat, so we would really appreciate your feedback here. We're always trying to make these trainings better and more impactful for everybody who listens in. So we appreciate everybody joining today, and we look forward to putting on more of these webinars in the future. If you do have questions later, feel free to email us. We're happy to get those answered for you.
Yeah, thank you all for taking the time. Really appreciate it.
Great, thanks everybody. This webinar will be posted on our website as well, and we'll share the link with everyone so you have it for later. Bye.